All right, so I will talk about a little bit of something that I've been doing with the Max Planck Institute right now. And the main person who is actually doing the work is Dakwon Yu at MPI. And we are working with the MPI, the new model is called ICON-XPP. And this is the future generation CMIP model. And my title, How to Train Your Dragon, is kind of, I want to indicate that this model is kind of a beast and it's hard to control. And you will see that I can also not control it, or we cannot control it. But we're trying our best to making some progress. So here's my outline. In principle, I don't think I have enough time to talk about this because this is a fairly complicated topic and I would probably need more than 20 minutes to explain it. But anyway, I go through this. The main focus here is to try to optimize the model parameters to make the ENSO and the coupled model better. But in order to get there, I need to explain a few things first, okay? Okay, first of all, introduction to tuning. I think many of you are aware of what it means, but I just want to lay out this a little bit in detail. And a few years ago, I wrote a paper about this, basically saying that I don't think tuning will work. But now I'm doing it, so you see it's a bit strange. So a climate model is a model of many models. They're all interconnected in a complex way. And so the climate modelers develop the submodels, and then they put it all together to get the coupled model. And then they start fine-tuning the submodels again within the coupled model. This is the kind of tuning I want to talk about, right? That you start to play around with model parameters of submodels to make the whole model work better. And the question is, can something like this actually work? And in the paper a few years ago, I'm basically arguing that this is not very efficient and it can work, but it has a lot of disadvantages. While the alternative, playing around with anomaly coupling, flux corrections, the community doesn't like at all, but actually it's far more efficient and it's far more, you get better outcomes in principle. That was the argument in my paper back then. So I'm not saying that you should do flux corrections. I'm just saying that tuning is likely to be really complicated and can potentially not work very well. But nevertheless, I'm doing this now with the Max Planck paper, mostly because that's something that everybody does. And since everybody is doing it, I want to try to see how we can do it maybe in an effective way. So the aim is to improve the model simulations by systematically tuning model parameters. And we start with an AMIP approach. So we simplify the problem a little bit because you see that the coupled model is far more complicated and it's not easy to tune. It's much, much harder to tune the coupled model. So we just want to show a proof of concept that it can actually work. And I will show you this, that this can actually work in a simplified setup. And by systematically, I mean a little bit unlike of what people usually do when they do tuning, and try to do this in a bit more systematic way. So the model that I'm talking about is the ICON-XPP. So that's the resolution of the atmosphere is 160 degrees, the ocean is 40 degrees. It runs about 80 years per day on the Max Planck computer. So this is fairly important because we are actually doing a lot of runs. So what I'm talking about are hundreds to 1,000 of perturbed parameter runs that we have done in the last year. And we also have a higher resolution version where we just double the atmospheric resolution and also double the ocean resolution. But most of the runs that I will be talking about are AMIP runs. So there's the atmosphere and 30 years of prescribed SST variability from observations. And this is basically, the idea is that this should help to develop the prototype for the CMIP 7 that is supposed to be starting next year or so. Okay, so when we want to tune the model, we have to have a matrix. And what we are defining a fairly well-defined matrix to evaluate whether we are better or worse. And this matrix is based on the Planton et al. Matrix, which is also, I think, installed at NCI. So basically what it does, it has a scale here, red is bad and blue is good. And each model, so here's a bunch of models, the CESM, which is a good one, the MPI, which is the one that we are looking at, the past MPI version. And then here's some CMIP averages and observations. And there's here on the x-axis lots of different matrices. So there are about 20 different parameters that this matrix includes. And I will talk about using some of them. So if you do so this is an overall scale here. So the average here is the CMIP mean average. So in the Planton paper, they basically have this bunch of 19 different CMIP5 and CMIP6 models, and they have basically ranked them. So up is bad and down is good. And then here the blue line and the red line are the average CMIP5 and CMIP6 values. So CMIP6 is slightly better. The observation is the reference. You cannot get there. This is by construction impossible to reach in this kind of matrix. For reference, another observation like ERA would get that close to observations. So this is theoretically, you can expect a good model or a model that is consistent with observation should be somewhat here in the yellow area. And you can see none of the models is in the yellow area, so none of the models is consistent with observations. The ACCESS model is the first bunch here. These are the previous generation ACCESS models. The best model is the ECS in this matrix. And the previous version of Max Planck wasn't that good in this matrix. And the current version that we started working on is currently somewhat here in the middle of the distribution. Okay, so just an example, a list of what are these matrices. So there are a bunch of them. So 8 of them are about the climatology of the tropical Pacific. Most of them are about precipitation, both in the mean and in the seasonal cycle. And then there's zonal and meridional means. So these are 4 different precipitation values. And there's 2 for equatorial SST, and then 2 for equatorial zonal wind stress. And then there's a bunch of variables describing ENSO variability, the SST variability, the things that you think of, amplitude, pattern, seasonality, skewness, and then the autocorrelation in terms of timescales. Then there's 5 ones about ENSO feedbacks, interaction between SST and winds and sea surface height and sea surface height and SST, and then the heat flux, and then something which I call residual, which is kind of the ocean tendencies of SST. And then there's 4 parameters about teleconnections. So I will not talk about all of these. I will simplify this. So we start with AMAP. So in AMAP, we really have only 8, because many of these, like the SST variability, we cannot evaluate. They are pre-described. And then the teleconnections I'm ignoring because I'm interested most in ENSO dynamics and not teleconnections. So we have just a limited number of parameters, 8 of them that we are discussing. Just an example here. This is the Pacific zonal mean precipitation. So here's the equator, southern hemisphere, northern hemisphere. Black is observed, blue is the control run, and red are a set of example simulations where we perturb a parameter. And you can see the model rains too much, specifically in the southern hemisphere. It has this double IQZ problem, like most models. Another parameter here is the Bjerknes feedback SST wind relationship. The black curve is what should be observed, and the blue is what the model does in the AMAP simulation. And you can see it varies, but it's not totally off in terms of amplitude, but it's a bit displaced. So based on this, we can basically take all of these 8 different parameters from the ENSO matrix that we can evaluate in AMAP run and then combine them to one matrix. Basically, I have these 8 things. So the first 2 are precipitation, another precipitation 2, and then climatology of the zonal winds, and then these 2 feedbacks. So we combine them all to one matrix, and then we compare them, what the observed look like with the control. And we normalize the scaling. So each of these would have different units. So we normalize them basically by how much the control run is biased to the observed. Sounds a bit artificial, but we have to somewhat normalize. Otherwise, we cannot put them into one matrix because we have to get rid of the units. And so then we can plot just the difference between the black and the blue curve. That is basically our bias, our error. So we're basically saying that this line ideally want to be straight 0, and we want to get rid of all the variations that we see in here. So we can normalize this and say that this error here, which is the error of our starting model, the control model, is an error of 1. So we have basically normalized this to say that this is an error of 1. And now we want to get this error smaller. That's the aim of what we are doing. Just for comparison here, here's the error of 1 of our AMAP control. The coupled model with the ocean has obviously a larger error, 1.5 actually in this case. So only on these 8 AMAP matrix, not on the whole set of Planton matrix, only the ones that I just showed you, the 8 ones. And these are a bunch of simulations where we have varied the parameters. You can see they spread, some are worse, some are better, but they vary a little bit. And we are aiming to get somewhere here lower values. Okay, in order to do this, we want to vary the parameters. We have to understand the sensitivities of each parameters, how the model would, if you change a parameter, how would the model change these ENSO matrix? So let's say here's an example. We have a parameter. I actually don't know what this is, but it's doing something to the convection or to the clouds. So we vary this parameter. These are the red lines. We have experiments done, 30 years AMAP simulation. Each one of them is one simulation. And we see by how much it actually changed the precipitation compared to the control one, which is a blue one. And based on this, we can actually define a sensitivity. We can say that for the given parameter, for the given matrix, our sensitivity as a function of, here in this case, latitudes, is basically the change in the physical variable, which is here precipitation, per change in parameter in these experiments. So in each of these experiments, we know by how much we have changed the parameter by a certain value, and then we can actually calculate the sensitivity. This is shown here. So the blue, for comparison, is just the observed difference of the control one. You can see by how big is the problem in the control one. And the red curve, the solid one, is our mean sensitivity based on these experiments. So we can see clearly here that it can change the precipitation here quite clearly in the northern hemisphere. And this is shown here that we have a sensitivity that is different from 0. We also have a sensitivity in the southern hemisphere, but a bit smaller, and almost no sensitivity on the equator. We can also see that if you compute the sensitivity for each individual parameter change, that this actually varies a little bit. This is the standard deviation that gives us some uncertainty. That means this is not linear, or not, the runs are not long enough, or we don't have enough statistics. There's some uncertainty in this. And the ratio here between how strong the sensitivity is and how strong the uncertainty gives us this ratio here. And this ratio is an indicator of how well do we actually know the sensitivity. If it's large, then it's a well-known sensitivity. If it's small, it's a less known sensitivity. Here's another example, a different parameter. It's called ice crit. I don't know what it does, but I guess it has something to do with ice in the clouds. You can see it has almost no impact on the rainfall, and therefore the sensitivity is basically 0. And then, so we have basically 0 sensitivity. The uncertainty is much larger than the sensitivity overall. Therefore, this R value is pretty small. So some of these sensitivities will be large, some of the sensitivities will be small. When you have different parameters, here are 2 different parameters, and I show you here the sensitivity for each of these 8 matrix. You can see they are actually different, but in this case, they are highly anti-correlated. So even though we have about 20-something parameters that we can tune, many of them do very similar things and are highly correlated to each other. If you do another 2 pair of parameters, you can see one of them has a strong impact, the blue one, but the red one has almost no impact. But therefore, it's not highly correlated. So that would actually be an advantage. So you can tune these 2 to get different results. But then here, another one, when you compare the first one here, ENSO, with another parameter, they both have big impacts, but they are also highly negatively correlated. So when you do these kind of parameter variations, you need to know what parameters can you tune, by how much can you tune them, and ideally you want to have independent parameters that do different things. But we notice here already that many of these parameters are actually doing very similar things. So when we look at the overall sensitivity, so basically these amplitudes here, how strong are the amplitudes? We can see the red one here has very little sensitivity, the blue one has much more. And then we can look this for all the 21 parameters that we actually worked with. You can see there's about 6 of them that have stronger sensitivities. And most of the other ones have very little sensitivities on ENSO. So ideally, you would think that these 6 parameters are the ones that can actually affect ENSO. Another thing to consider is that we do this on a fairly low resolution model. And ideally, you would think if you do this on a low resolution model, do you actually benefit anything for the higher resolution model? And hopefully you would have some benefit for the higher resolution model. To test this, we run our AMAP run in the low resolution, and then we do it again in the high resolution and do these sensitivity tests again. And we do this only for a few parameters to test whether this works. So here I've done 1 parameter, and I've done the sensitivity for the low resolution, which is the red curve. And then we have estimated the sensitivities for these 8 matrices in the higher resolution. And you can see they are highly correlated. not in all individual parts, like say here in the last one, which is the heat flux SST relationship, they are not highly correlated. But in most of the other ones, they are doing very similar things. That means what you learn from the low resolution actually does have some benefits for the high resolution. But correlation is 0.7, not super high. Here's another parameter, this PR0, and you can see it's also highly correlated. And then here for the wind SST relationship, maybe they are not doing exactly the same thing, but somewhat the same thing. So in other words, these sensitivities approach could actually work, that you gain at least a little bit of knowledge for also the higher resolution, which has a benefit that you can use the lower resolution, which is cheaper to figure things out and then apply it to the higher resolution. Okay, so we have now a way to estimating parameter sensitivities. Maybe I should formulate my cos function. So our cos function is formulated this way. So the cos function is some. Yeah.
Can I quickly ask something on the last point? What were the different resolutions that you looked at?
Oh, the different resolutions is twice the resolution. So this resolution is 160 degrees in the atmosphere, and this one is 80 degrees in the atmosphere. 160 kilometers in the atmosphere, and this one is 80 kilometers in the atmosphere. So we doubled the resolution horizontally, and I don't know what's happening vertically, but horizontally the resolution is doubled.
And would you expect a similar result if you go to even higher resolution, where you resolve more of like mesoscale?
No, I would expect that first of all, the higher. So in general, when you increase the resolution, you have to also change the parameters. People don't just change resolution, they often also change the parameters. So I don't know from these 21 parameters, how many of them actually can have an equivalent at higher resolution. And I'm pretty sure that at some point convection is turned off and then many of these parameters are irrelevant. So I would expect that the further you go away from the resolution on which we developed these, tested these sensitivities, the less value they would have. But we do see here at least that if you double the resolution, you can at least assume that there's some similarity. But I would assume that the further you go away, the more this will not be true.
And it might not be like a linear relationship, but then you get jumps.
Yeah, it's actually, I mean, initially we thought that this will have no relationship, that it's, nobody expects this to be linear at all. And the surprising thing is that it's actually highly correlated, which I think is good news, because this means you can use a lower resolution model to learn something about the higher resolution model.
Okay, thank you.
So just a super quick one while we're here. You said you're tuning 21 parameters. How did you choose those 21 specifically? That was something that MPI had already done, or?
Yeah, so it's kind of expert knowledge, right? So these are the usual suspects, right? So we asked what should we tune, and then they gave us a list. And then the next question we asked is how far can we go away from the current values? That is actually the more tricky question, and there's some uncertainty on this. And some people give ranges that are just not doing anything, and then some people give other ranges. So it's a bit of uncertainty in this. So you will see what we present here is certainly nowhere near perfect. This can be done much better. This is really just a first test of seeing whether this would go anywhere. And I think in reality, we have to do this much better. And I will come back to this at the end. How much time do I have? Okay. And the cos function. The cos function basically is what we try to minimize. So the way that optimization works, you have a value of which is bad, and you want to make this value as small as possible. So this is the value we want to make as small as possible. And it has three elements. The first one is just the matrix that I just showed you. So we want to make this blue curve go to 0. So this RMSE value has to goes to 0. This is our main thing. And we achieve this by changing the parameters. So initially, the parameters are all normal control values, and the deviation from these control values we sanction. We don't want these parameters to deviate from the control values, but we do this with a power of 4. That means we can make small changes that will have no effect, but if we go far away from the control values, then this is not good. So we want these parameters to not go far away from the control values. That means initially this part here 0, and this part here is 1, and by reducing this one, we will increase this one to get a balance. Right? And at the same time, we have limits. So these parameters that we have cannot be negative. None of them, so they're all defined in a positive way, so none of them can be negative. So whenever one of these parameters get negative, we double this value of of limit. That means this cannot happen. So immediately when one of these parameters in the optimization scheme is chosen to be unphysical, then this is sanctioned in the cost function. So in principle, to actually calculate these ENSO matrix, you would have to run the model every time. And if you want to figure out what does any parameter combination does to the model, we have to run the model. And this is very expensive. And this is a key thing. So we are not doing this. So instead, what we are doing is we try to approximate what the ENSO matrix would look like by using the sensitivities that we have calculated. And that works this way. So we estimate the ENSO matrix by this linear superposition. So we make a linear superposition of all these tuned parameters. Here are the parameters that we have changed. And if we change a parameter, assuming they have a sensitivity, they would change then the ENSO matrix. And we sanction, so basically we have here a sensitivity, which is the red curve. We multiply it by how much we're actually scaling it. And then we also consider the uncertainty. So this uncertainty ideally is a large, this is actually not an uncertainty, this is a certainty. So if this value is large, we know very well what the sensitivity is. If this value is smaller than 1, then there's some uncertainty. And if there's some large uncertainty, then this value gets small, and we do not really do much with these parameters. Does this work? So we tested this. So we run a few 21 perturbed parameters. We run the model. So this is a red curve, and estimate the matrix. And this blue is what we approximate by this equation that I just showed you. And you can see, surprisingly, this is not completely unrelated. Surprisingly, there's a positive correlation. I say surprisingly because obviously all of these parameters are highly nonlinear functions. And if you perturb 21 parameters, you would expect that this linear superposition should not work at all. But actually, it does have some skill. So you can see in some of these parameters, actually, they're very similar here in the rainfall. What's not so good is always these seasonal cycles. They are very chaotic, except for this one here in the wind stress, the season cycle works. So that's actually a positive correlation, which is good news. That means this approximation is not completely crap. Here's another one where we did this again, another set of 21 perturbed parameters. Correlation is a little bit lower. And then here's another one where the correlation actually is basically 0. And you can see it is really bad in the heat flux SST relationship, but in the wind SST relationship, it's pretty good. So there's no guarantee that this works. Actually, this approximation is really just a kind of kind of very simple approach to have a guess without running the model. But it's not with 0 scale. So it does work somehow. So now the optimization. So the optimization, we have tried to optimize 21 atmospheric parameters. The optimization scheme that we use is the so-called Nelder-Mead optimization scheme. That is a very widely used, simple optimization scheme. By no means perfect, and I'm pretty sure that we can do much better. So it finds a minimum in the cost function of a high-dimensional nonlinear function, and it basically varies the parameters in some kind of systematic way, and it needs about 1,000 variations to figure out what is the optimal parameter combination. So in principle, you would have to run the model 1,000 many times to figure this out, and one after the other. So this would, if you run the model, it would take ages, and this is why I've done these approximations. So this is why we're doing this with an approximation of the ENSO matrix without running the model. But in principle, in optimization scheme, you would need to run the model. But we have done the cheap version, and we just wanted to test how far can we get with this cheap approach. So here's the outcome. So black was our initial run, and red is our optimized run. And you can see for every single parameter, we more or less get closer to 0. Maybe not this one here, but the rainfall get closer to 0, along the equator as well. The feedbacks get closer to 0. That means they are all better. And the RMS error gets from 1 to 0.6. So we have almost half the bias. But you can also notice that the red and the black curve look similar, which basically means that the biases are still kind of the same. They are just smaller, but they're still the same kind of biases. But we have substantially reduced them. So in this initial graph that I showed you here, where you had this error of 1 and the covered model, which has an error of 1.5, we now get to about an error of 0.6 with this optimization. If I go back to my, if we double the resolution in the AMAP, you get to this point here. So increasing the resolution also obviously makes the model better, but actually the optimization in this case could make the model improve the model more than just doubling the resolution in the atmosphere. If I get back to this initial graph here of this overall ranking and where the good models are, if we are super optimistic and what we just did, we would actually end up here. Assuming that this could be transferred into the coupled model, we would actually end up with a good model, really we get to the yellow range. But obviously what I just showed you was just the AMAP and it wasn't the coupled model. So it's an unfair comparison, but I'm just saying in an optimistic interpretation, this kind of suggests we could potentially get to this point if we do this kind of optimization on a coupled model approach. Okay, but how about the coupled model? Is it actually working for the coupled model? You can probably guess that everybody who knows coupled model knows, of course, that this doesn't work in a coupled model. So here's just one metric, equatorial Pacific mean SST, and the black is observed. So it's cold at the east and warm in the west. And here's a bunch of the coupled models. This blue or the red one are kind of the reference, and there's many different versions. You can see all of them have a cold tongue bias, fairly severe cold tongue bias, and then have a warm pool here in the east. And this is what happens if you use the optimized parameters from the AMAP run. You suddenly warm up your model by 8 degrees, and that's globally basically. So it has a huge impact, but surprisingly, even though we completely boil the global climate and make it much, much warmer, the ENSO metrics are actually a little bit better in the coupled model as well. Not much, very tiny little bit. But at the same time, obviously there's something happening that you don't want. And we are, of course, not surprised by this. This was kind of an expectation that something would blow up. In this case, what blows up is the heat flux. So some of these parameters that we played around with actually have a very strong impact on the net heat flux. So this is a Pacific zonal mean net heat flux, and the sensitivity is an average about 8 watts per square meters. So by changing this parameter by about a value of 1, you basically get 8 more watts, negative 8 watts into the Pacific Ocean, and that's more or less global. So clearly, this is not what you want to do. So some of these parameters have strong impacts on things that are not controlled by the ENSO matrix. So obviously, which comes with no surprise, is there are aspects that you need to consider when you go into the coupled model that are beyond the ENSO matrix. And that is obviously what makes this coupled modeling much, much more complicated. Another point to make is if you go from the AMAP to the coupled model and you do try to calculate these sensitivities again. So this is what I showed you for the AMAP. Now let's do the same parameter and do the same kind of perturbations in the coupled model and see what the unsensitivities are. You will then notice that the same parameter perturbed in the coupled model has suddenly no sensitivities. Right? So parameter that in the atmosphere run changed the rainfall quite substantially, and that would be a good tuning parameter to improve the rainfall. Then in the coupled model, suddenly it doesn't do this at all anymore. So in the coupled system, the sensitivities are substantially changing. And I think this indicates that the mean state biases are actually, which has been mentioned in many, many studies before, but I also published on this. But it suggests really that the mean state biases in the coupled models are actually the bigger problem than these sensitivities. Because otherwise, how could you explain that this parameter, which does a lot in the atmosphere, but then suddenly in the coupled model doesn't do anything? So that was all of what I want to present. So still a minute left, so just a summary. So our approach works in the AMAP run. Not perfect, but it does work. There we can estimate the sensitivities to each of these parameters. We can actually approximate what would happen to these parameters by a linear superposition. It doesn't work perfectly, but it actually works a little bit, which is surprising, I think. The low resolution sensitivities are actually similar to the higher resolution, which is really great because that means you can use the lower resolution to develop your model. But clearly the biases, they will still remain, and they reduce the biases, but they cannot get rid of it, at least not in this approach that we did. The coupled model is far more complex, and what we did here so far is little improvement of the coupled model. I mean, it does help, I think, to understand the coupled model problems, but far more complicated. There are many more aspects to consider than just the ENSO matrix, obviously, in the coupled model, and the sensitivities in the coupled model will be very different from the AMAP run. And the mean state biases appear to be dominant. I think this is what the reason. So the reason why the sensitivities are so different from the AMAP, I think, is because of these large mean state changes that you will see in the coupled model. And in terms of an outlook, can such tuning work? I have always been very skeptical on this, but let's start with the positive, the upside. You can strongly improve the model performance, I think. So if you think about the sketch here where the good models should be, I think you can get there with tuning in theory. So if you can do this, then you have actually a much faster model, and so you can improve the model without increasing the resolution. I strongly believe that this is true. And much better schemes than what we just did are possible. So this is really just a crude first guess what we did. But you would need much more resources to actually do this compared to what we just did in the last about half a year or so. And it's basically just 2 people who did this. So the downside is this is really a highly complicated problem. There are many, many parameters. There are many, many matrices, and it is really, really complicated. And it needs really a lot of computing resources. So we did about 1,000 runs. Probably, I think you need more than 1,000 runs to do this. And so it really needs a large computing resources. And it also has a disadvantage that if you start this kind of tuning, and I think it has been mentioned in the literature in the past, you will artificially make all these models depend on each other. So every time you develop a submodel that is new, you would have to do this whole thing again. And it really requires a team effort of climate and math experts to know how to do these kind of things. All right, that's it. Thank you.